so this video is about radicals and dealing with things, putting them in simplest radical form. So when we look at something with a square root symbol, we have some terminology we need to talk about. So you know this is a square root symbol, or your fruit sign. This number up here is what we call the index. And now if you're looking at a square root, you don't always have an index, but sometimes it's a cube root or a fourth root or a fifth root, in which case you do have an index. So this is actually very important. This number under here, this term is called the radicand. And the number that you get, the resulting term, is called the root. Alright, so let's look at some examples. So you know the square root of 81 is equal to 9, because the square root of 81 is equal to 9 times 9, or 9 squared. And 9 squared is just 81. Alright, the cube root, notice this time I changed my index to 3. Cube root of 64 is 4, because 4 times 4 times 4 is equal to 4 cubed, which gives us 64. Alright, the fifth root of 32x to the fifth is 2x, because if we took 2x times 2x times 2x times 2x times 2x, which could be written as 2x to the fifth power, which you know is like distributing 2 to the fifth times x to the fifth. That gives us 32x to the fifth. So that's just breaking this down, how we deal with radicals. Again, our index and our radicand. So what if I said we were going to learn to take simplest radical form? Let's say we wanted to find the cube root of 24. Now, you probably know 24 is not a perfect cube, because you know that the number 27 is, right? Because this would be 3 times 3 times 3. And now if I asked you for the 2 times 2 times 2 is the next closest one, and 24 falls in between the two of those, so without getting a decimal, you're not going to be able to get a perfect cube from 24. So we go back and we think about factor trees. So if we broke 24 down using a factor tree, we could say 8 times 3, well 3 is prime, so we could circle it, and we could break 8 down into 2 times 4, 2 is prime, we could break 4 down into 2 times 2. So if we were making a factor tree of 24, we could write it as 2 cubed times 3. Well, now I have something that is a cube root. So I could say that I wanted to take this, the cube root of this. This is the same thing as taking the cube root of 24. So what I would do now would be to pull out anything that is a cube root. Well, I could have the cube root of 2 cubed. I would write it out here, and then I would leave my radicand with my cube there, my marker's dying, and I would leave my 3 underneath. So the cube root of 24 is 2 cube roots of 3. It's kind of like dividing and getting a remainder. So let's review. How did I find my number in simplest radical form? I used factor trees to find the prime factorization. I pulled out any perfect squares, and any remaining numbers or variables stayed under the radical. Alright, so let's do a couple more examples, and we're going to hope my marker doesn't die. So let's say we want to find the square root of 12. So again, it's not a perfect square, because we know 9 is a perfect square, 16 is a perfect square, 12 is not. So if we used a factor tree, break it down, think about what perfect squares form it. We know that 12 is 4 times 3. Remember, I'm thinking of perfect squares. This one doesn't have an index, but if it did, it would be a 2, so we're looking for a square root. 3 is prime, 4 is 2 times 2, so we could rewrite this as the square root of 2 squared times 3. Now, pull out anything that is a perfect square. 2 squared, so I'm going to get 2 square roots of 3. And I'm done. I forgot to write something here. So, let's make up a problem. How about we take the 4th root of 64. So, if we made a quick factor tree of 64, doing 4th roots, I know that 64 is equal to 16 times 4. And I know that 16 is 4 times 4. And I know that 4 is 2 times 2. And this is 2 times 2. This is 2 times 2. And I may have messed up here, but 1, 2, 3, 4, 5, 6. Just 2 to the 6. But what if I broke this down to something that can be made a 4th root? I can leave it here. I can say, haha, this is, no. 2 times 2 times 2, 2 times 2 is 4 times 2 is 8 times 2 is 16. So 2 to the 4th power is that. So I would say 2 to the 4th power times 4 gives us that. So I can leave it right here just for the sake of this problem. Both of this we can take the 4th root of, sorry, and 4 I can leave under it because you cannot take the 4th root of 4. So the 4th root of 64 will be 2 4th roots of 4. Sorry, for a minute I was thinking square roots. So don't make the mistake that I did. Look at what your index is. This matches up. Now, what about this one? 18x cubed. We're looking for the square root of this. So we want to break 18 down and x cubed down into something we can take square roots of. 18 square root wise, break it down into 2 and 9. 9 breaks down into 3 and 3. So we want to break this into 3 squared times 2. X cubed, and this is where it gets new to you, breaks down into x squared times x. We've never made factor trees with variables before, but keep in mind that variables, when you're breaking them apart, variables with the same base, you add the exponent. So to get x cubed, you would do x squared times x to the 1. So x squared times x to the 1 would give you x cubed. So here, you can break this down to this, and you're taking a giant square root. Now, pull out everything that has a square root. Well, 3 has a square root, so I'm going to write 3 on the outside. Cross it out. X has a square root, so I'm going to write x on the outside. Cross it out. What's left under my radical? 2 and x. So 18x cubed becomes 3x square root of 2x. Now, you have some more left in your notes. Please work on those, and we'll go over them in class tomorrow.